How do graphics cards work? Exploring GPU architecture in detail. Introduction. Graphics processing units, GPUs, commonly known as graphics cards, are specialized hardware designed to accelerate rendering and computation for graphical and parallel processing workloads. Unlike central processing units, CPUs, which are optimized for sequential task execution, GPUs are highly parallel, making them ideal for handling large amounts of graphical data and complex computations. This article explores the architecture of GPUs, their working principles, components, applications, and emerging trends in modern computing. 1. Understanding the basics of a GPU. A GPU is an electronic circuit that rapidly manipulates and alters memory to accelerate the creation of images in a frame buffer intended for output to a display. While initially developed for rendering graphics, modern GPUs are also used for general-purpose computing, GPU, artificial intelligence, AI, and scientific simulations. 1.1 GPU versus CPU. A CPU consists of a few cores optimized for complex task execution, whereas a GPU has thousands of smaller cores optimized for handling multiple tasks simultaneously. This difference makes GPUs superior in parallel processing, crucial for graphics rendering and machine learning tasks. CPUs excel at handling sequential tasks, managing operating systems, running software applications, and executing instructions that require high single-thread performance. On the other hand, GPUs are optimized for massively parallel workloads, processing thousands of operations at the same time, making them ideal for rendering graphics and performing AI computations. Modern CPUs include multi-threading and higher clock speeds, but GPUs offer significantly greater throughput when handling massive datasets, such as rendering 3D environments, performing simulations, and training AI models. While CPUs continue to be the backbone of computing, GPUs have become indispensable for advanced computational tasks. 2. The evolution of GPU architecture. GPUs have undergone significant transformations since their inception. The key phases in their development include 1. Early GPUs, 1980s–1990s. Early GPUs, such as the VGA and early 3D accelerators, focused primarily on basic graphics rendering. 1. The introduction of GPUs like the 3DFX Voodoo series revolutionized gaming by bringing 3D acceleration to consumer computers. 2. The rise of programmable shaders, 2000s. The introduction of programmable shaders in GPUs, such as NVIDIA's GeForce 3 series, enabled greater flexibility in rendering effects. 2. Developers gained the ability to write custom shader programs, significantly improving graphics quality and realism. 3. General-purpose GPU computing. 2010s, CUDA and OpenCL allowed GPUs to handle computational workloads beyond graphics. 3. With frameworks like NVIDIA's CUDA and AMD's ROCm, GPUs became powerful tools for scientific research, engineering, and AI training. 4. AI-optimized GPUs, 2020s present. With the explosion of deep learning and AI, modern GPUs incorporate tensor cores and ray tracing cores to support AI-driven applications. 4. NVIDIA's Ampere and Ada Lovelace architectures have pushed AI inference and graphics rendering to new heights. 3. Key components of a graphics card. A graphics card comprises several essential components that contribute to its functionality and performance. 3.1 Graphics Processing Unit, GPU, the heart of a graphics card. The GPU itself consists of 1. Streaming multiprocessors, SMS, groups of processing cores that execute parallel instructions. 2. CUDA cores, stream processors, the basic execution units responsible for computing pixel transformations, shaders, and AI workloads. 3. Ray tracing cores, specialized hardware for real-time ray tracing, improving lighting and shadow realism. 4. Tensor cores, hardware dedicated to deep learning tasks, accelerating AI-driven computations. These processing units work together to execute millions of instructions per second, allowing the GPU to handle complex rendering, physics simulations, and even scientific computations. The number of CUDA cores or stream processors directly impacts a GPU's computational power, with higher-end GPUs featuring thousands of such cores. 3.2 Video memory, VRAM. VRAM stores textures, frame buffers, and intermediate rendering results. High-speed memory types like GDDR6 or HBM ensure smooth rendering without bottlenecks. Modern GPUs feature memory capacities ranging from 4 GB to 24 GB or more, depending on the target market. Higher VRAM allows the GPU to store larger textures, making it essential for gaming at high resolutions, professional 3D rendering, and deep learning applications. HBM, high bandwidth memory, offers improved energy efficiency and bandwidth compared to GDDR memory, making it ideal for workstation GPUs used in scientific computing and AI training. 3.3 Memory bus and bandwidth. The memory bus determines the speed at which the GPU can access VRAM. A wider bus, e.g., 256-bit versus 128-bit, and higher bandwidth allow faster data retrieval, enhancing performance. Memory bandwidth is crucial for high-performance applications, as insufficient bandwidth can create a bottleneck, limiting a GPU's ability to process large datasets effectively. 3.4 Cooling system. GPUs generate significant heat, requiring cooling solutions like 1. Air cooling. Fans and heat sinks dissipate heat. 2. Liquid cooling. More efficient but expensive cooling method using a closed-loop or custom water block system. 3. Hybrid cooling. A combination of air and liquid cooling to maximize thermal efficiency. Cooling efficiency directly impacts a GPU's performance, as thermal throttling occurs when a GPU overheats, reducing clock speeds to maintain safe operating temperatures. High-end GPUs often feature multiple fans and advanced heatsink designs to dissipate heat effectively. 3.5 Power delivery system. Graphics cards require substantial power, provided through PCIe slots and additional power connectors, e.g., 6-pin, 8-pin, or 1.2 VHPWR. A robust VRM, voltage regulation module, ensures a stable power supply to the GPU. Power consumption varies across GPU models, with high-performance GPUs requiring upwards of 300 W, necessitating a high-wattage PSU, power supply unit. 3.6 Display outputs. Modern GPUs support multiple display interfaces like 1. HDMI, common for TVs and monitors. 2. DisplayPort, supports higher refresh rates and resolutions. 3. USB-C, Virtual Link, used in VR headsets. These interfaces allow for multi-monitor setups, 4K and 8K gaming, and high refresh rate displays crucial for competitive gaming. 4. Applications of GPS. GPS are widely used in various industries, including 1. Gaming, rendering complex 3D environments and high frame rate gameplay. 2. AI and machine learning, training deep learning models for natural language processing, image recognition, and data analytics. 3. Scientific computing, performing simulations in physics, chemistry, and genomics. 4. Medical imaging, enhancing MRI and CT scan analysis. 5. Cryptocurrency mining, processing cryptographic algorithms for blockchain transactions. 6. Autonomous vehicles, powering real-time sensor data processing and decision-making. 5. Emerging GPU trends. 5.1 Real-time ray tracing, improving lighting, shadows, and reflections in gaming. 5.2 AI-based super sampling techniques like NVIDIA DLSS and AMD FSR enhance resolution using AI. 5.3 Cloud gaming and GPU virtualization, enabling high-end gaming and computing on remote servers. 5.4 Energy-efficient designs, reducing power consumption for sustainable computing. 5.5 Neural processing units, NPUs, specialized AI accelerators integrated into GPUs. 5.6 chiplet-based GPUs modular design allowing scalability and improved efficiency. 5.7 quantum computing and GPUs exploring hybrid models for advanced computing applications. Conclusion: graphics cards have evolved from simple rendering tools to powerful parallel processors capable of handling diverse workloads. Understanding GPU architecture helps in making informed choices when selecting hardware for gaming, AI, or computational tasks. As technology advances, GPU